0 is equal to lambda times y, right? Right? That would be the case. Now, each of those are two different scenarios, aren't they? So let's look at this. Right? This means that either x is 0, right, or lambda is 0. Yeah, so you see that if for this to be true means that x or lambda has to be 0, but this is already a contradiction, right? This is a contradiction. Remember, that's how we write contradictions, right? This is two arrows hitting each other. It's a contradiction because we started this off assuming that x wasn't 0, right? So it can't be that. That means what? Lambda must be 0. So lambda has to be 0 now, right? Lambda is 0. So we got to go down this road. Same thing with this one, right? These are two different scenarios. If y is 0, then we get a contradiction. And that means that lambda must be 0. Okay. Let's try to kind of recap here. What we're saying here is that x isn't 0, y isn't 0, z is 0, and what is this forcing to happen? Lambda has to be 0, right? Lambda has to be 0. Yeah? I'm going to continue now. So lambda must be 0.
You don't need a new little suppose symbol?
You could. You could say, okay, you want to say suppose lambda is 0. I'm still working within this framework, right? Suppose this and all of that forced this to happen. So now let's suppose lambda is 0. If lambda is 0, what does equation 1 tell us?
Well, we're still supposing that z equals 0 too, right?
Yes.
So 0 equals 0.
So 0 is 0. So equation 1 is satisfied. So equation 1 is good. Okay, comma. What about equation 2? Good, right? Equation 2 is good. 3, yeah, 3 I think is where we got all this from because z is 0, right? Boom, z is 0. Equation 3 is good. All right, which leaves us with the last equation. What's the last equation? This one right here. Z is 0 though, right? So equation 4 tells us x squared plus y squared must equal 1, right? That's a circle. There's an infinite number of points, right? So what now? What now? Are y'all starting to see how this gets really complicated because you're like trying to keep track of what you're doing, right? All right, so we already know what happens here. If they're not all 0, we know what happens, and life was actually pretty freaking good here. But now, this, we're like, what the right? That's what we're saying. Like, how are we going to do this? How are we ever going to check? Look, all the equations are satisfied, and the fourth one has two variables in one equation. There's an infinite number of answers.
Is that our new constraint, and we can get rid of equation 3?
Not quite. There's something even that we could have seen even at the very beginning when we did this assumption right here. Something about our original function.
Well, z equals 0, and the original function is 0.
If z is 0, the original function is 0, which means that yes, these are all places where we're either going to have a max or a min. But guess what? At any of these places, z is 0, and so plugging 0 into this, you get 0. So do y'all see that on this circle, right? On this circle, f of what? Whatever that is, the point x, y, z, whatever that point is, x, y, z, that's 0. Because z is 0, right? I should put that in there. Z is 0 because of this. And now that you think about it, you know how there was all these different cases we need to look at? Like, okay, what if x is not 0 but both of these are? Well, guess what? If any single one of these variables is 0, then the value of the function is 0. So we're actually done. Now I'm going to write it down though. I'm going to say after this, I'm going to say
Does that not technically make it our min?
Pardon?
Does that not technically make it a min? Minimum?
Make- What did I say?
Well, you said just like, does that not technically make 0 a minimum?
Well, we had a maximum. We had another number earlier, didn't we? 1 over 27.
Yeah, but they all of them were 1 over 27, so that was only a max. So 0.
That's right. 0 is the min.
Okay.
Yep. So, but I need to say here, I'm going to say, suppose any single variable is 0, right? So it doesn't matter. What I'm saying is x can be 0, or if you have y equals 0, or if you have z equals 0. Doesn't matter. If any one of these is 0, then the function's value there, right? The function's value is going to be 0. And so I know that this is a min. Where does it happen? All over the place. There's minimum values, right? It doesn't happen in a single place. It happens at multiple places. Unfortunately, I can't show this to you, right? I can't show you. But anywhere where your x is 0, y is 0, or z is 0. Okay, maybe I can show it to you in a certain way. Remember, the domain is a sphere of radius 1, right? What if I take that sphere and I say z is 0? Z is 0 would be what? Circle, right? Circle on the ground. If you take any point on the circle on the ground and plug it into this function you can't see, you're going to get 0. If I let y be 0, now it's like, what, the circle this way or something? Any point from that circle and you're going to get into the function a 0. And there's one more if you turn x is 0. So on those 3 circles, this one, right, this one, that one, and that one. Those 3 circles, you plug in any points on those 3 circles and you're going to get 0 in your function. All right. Yeah, we're not having fun yet? Cal 1 problem. I think it's a Cal 1 problem. Let's see. Find the maximum volume of a rectangular box that does not have a lid if it is to be made of 12 square meters of cardboard. What are its dimensions? So the idea here, I have to draw a picture that goes with this. You have a box. Like this. And it has an open top to it, right? Find the maximum volume of that box with no lid if it is to be made of 12 square meters of cardboard. So all I'm telling you is that the total surface area, right? You're only allowed to use 12 square meters of cardboard to make this. But I want you to make it in a way that has the most volume possible. Okay, so we're trying to find the maximum of what? The volume, right? We were just finding maximums of functions, right? So this is good. We're going to find the maximum of this function. When it comes to a box, if I call this distance from here to here x, I call this distance from here to here y, and I call this distance from here to here z, then the volume of this is pretty simple, isn't it? The volume is just x times y times z. I'm going to say the volume is a function of 3 variables. It is just x times y times z. Isn't it? The volume is a function of 3 variables, x, y, z. I would like to know how big this could possibly be, right? What's the biggest this could be? But there's a constraint. What's the constraint? I can only use 12 square meters of cardboard. That's the surface area, isn't it? Tell me the surface area of this thing. I'm going to say SA for surface area. The surface area must be 12, right? Okay. So you'll have this area right here. What's that area right there? X times Z, but then you have the one on the back. So you have 2xz's plus, okay, now you have the base. Are you doing the base? The bottom of this thing right in here, right, that you can't see down there, but that's xy, right? Plus xy. Plus, you have the two sides over here, right? This side and that side. So that's 2yz. That's it, right? Okay, so do you see how this ties exactly into what we've been doing? You have a function of three variables. You want to find its maximum or minimum. We don't care about minimum here. We want maximum of this, right? Subject to this constraint. The constraint is this. And so now we should be able to do this with Lagrange. So let's do this. Equation 1. The derivative of this function with respect to x, yz equals lambda, derivative of that with respect to x. Careful. 2z plus y. Okay, I put it in parentheses there. That's important because that's in front of lambda, right? That's my first equation. Second equation, partial of this with respect to y, xz equals lambda and then x plus 2z, right? Is that what you said? That's the derivative of this with respect to y. Third equation, xy equals lambda. Now differentiating with respect to z, 2x plus 2y. And then our fourth equation is a constraint, isn't it? Fourth equation is that one. Any questions on those? We get these partials right? 2z plus y. And with respect to y, it should be x plus 2z. And with respect to z, it should be 2x plus 2y. Okay. Now, hey, look at this function here. Can we agree right now that if x, y, or z are ever 0, then it's volume of 0, and that's like probably the minimum, and that's not even something we're concerned about. So I'm just going to put here, suppose x equals 0, or y equals 0, or z equals 0, then in that case, any one of those cases, the volume is 0, and quite frankly, I don't give a shit about that, because I'm not looking for a box with 0 volume. I mean, there's got to be a better way to do it, right, to get a maximum volume. That's a sad face over there. Or happy. I guess happy, because we don't have to consider them, right? Okay, so that means we have to assume that all x, y, and z are all not 0, right? All of them not 0. So I think we should maybe start with that assumption now, right? Supposedly. It might not. Yeah, we could probably assume that, because if lambda is 0, right, then one of these has to be 0. Yeah, so I'm going to say here, suppose that x is not 0, y is not 0, z is not 0. And if you want, you can put lambda here. I'm going to put it in a different color because I don't think you need it. You don't need to say that right now, but I'll put it there, all right? Okay, if they're not all 0, then I can do a lot of things, can't I? Now I'm going to do something on this one that I didn't do on the last one because y'all didn't mention it, but I'm going to do it on this one. All right, check it out. Do you agree that this, and this are pretty close to one another? They're all just like missing a letter. So what I'm going to do here is I'm going to multiply this side by x and then this by x. This one I multiply by y, multiply this by y. This one by z, and this one by z. Now, I can do that because x, y, and z are all not 0. So I can multiply both sides by x and y and z. It's not going to be illegal. So if I do that, do you all see that the left sides of all of these are the same? And now I can set this equal to this, right? And I can also set that equal to this. Okay. So if I do that, then what I can do, I'm kind of skipping some steps here just for time's sake. What I can do is I can say that lambda x times 2z plus y equals this one, lambda y x plus 2z. So that's me setting equation 1 and equation 2 equal to one another, right? And can I divide out the lambdas? Yeah, we can go ahead and divide it. So yeah, maybe that was good to say lambda is not 0 because we can do this step. Let's get rid of the lambdas. Let's distribute. So I'm going to get rid of lambdas, both sides, and let's distribute through. 2xz plus xy equals xy plus 2yz or zy. I see xy on both sides, which means it goes away. And I see a 2 on both sides. That can go away as well. So what does this become? xz equals yz, and I can divide both sides by z. Z is not 0. This means x is y. Ooh, that's good news. That's good news. Okay, now let me set the second and third equations equal to one another and see if something good happens. Okay, if I set the second one together equal to the third one, I get lambda y x plus 2z equals lambda z 2x plus 2y. Very similar sort of attack here, right? Kill the lambdas off. xy plus 2xz equals, I killed the lambdas, equals 2xz plus 2yz.
The first one would be 2yz, not 2xz.
2, wait, which one?
You said xy plus 2xz.
When
you distributed the y.
Oh, right here. Yes, thank you. Okay, does anything go away? Yes. We do get, okay, and that's what goes away, right? Okay, that goes away. And so you get xy. This time you can't get rid of 2 yet. 2xz. But you can get rid of the x, so you get y is 2z. So y is 2z, but y is also 2x. Y is also x. This is actually working out pretty good, isn't it? What now? I know x in terms of y or y in terms of x, and I know z in terms of y. Let's go to the last equation. We can write this in terms of all one variable. Which variable do y'all want? Y? I say y. Let's go with y. I like that. Okay, so I'm going to equation 4. I'm just kind of out of room and I'm all over the place here. I apologize, but I'm trying to get it on camera. So, all right, I'm going to replace everything in terms of this equation, all in terms of y. So 2x was y, so 2y, and then z was, I'm going to have to solve this, yeah. So 1/2 y is z, right? So I'm going to replace this with 1/2 y plus x, which was y, times y, plus 2y times z, which was 1/2 y equals 12. Now we just simplify. 3y squared? 3y squared equals 12. Y is plus or minus 2. Y is plus. And I think we can throw out one of those answers right now. Because y being negative 2 doesn't make any sense in my picture, does it? So I can throw it out. So I'm only going to look at y as 2. So I think I'm ready for a candidate here for my x, my y, my z, and my lambda here. We're saying y is 2, right? If y is 2, what's x? 2, and then z must be 1, and then lambda I really don't care about, but there it is. And is that going to be a max or a min? Got to be a max, because we already know if you let x, y, or z be 0, you get a volume of 0, right? Oh, but can you let x, y, z be 0? Yeah, look, if I let x be 0 and y be 0 into this, is there a solution? If I let x be 0, you get a solution. It's not a box, but I mean, that's the extreme, right? The volume is 0. So that's how I know this is a max. So what is the volume at 2, 2, 1? Should be this, right? 2 times 2 times 1? 4. 4. Now, what are the dimensions of the box? That's the last thing. We want this to be 2 meters by 2 meters by 1 meter, right? It wasn't z? Z was half of y? Yeah. So if I do a 2 by 2 by 1, I'm going to get a 4, it'll be 4 cubic meters of volume, right? 4 cubic meters of volume. And I will use exactly 12 square meters of cardboard. And that's the most I'm ever going to get out of that much cardboard.
That's a lot of cardboard.
Yeah.
2 meters by 2 meters by 1 meter? That's a big ass box.
Yeah, it's a big box. But it could be inches. We could change the whole thing to inches, right? All right. What do you think? That shows you, how you can use Lagrange. I don't know how you do this problem in Cal 1, actually. You can't. You have to get it all to a single variable, which is really hard to do. To get this to a single variable, how do you get this to a single variable? I don't think you can. Right? You can't. You did, but it was like you take a piece of cardboard and you cut the corners out and fold things up, and then that created relationships between the sides. Here, this is completely arbitrary, right? Only that it has to be a box. So much more powerful technique. All right, let me see. I think we should stop. I want to talk about the test. Are there any questions that you have about the test? Other than like, how do you do this problem? Have y'all had a chance to look at the review? Everyone, how does it seem to you all? Yeah?
What did you say about the reference? Should have been allowed to bring the
Yeah, so what I want everyone to do is when you come in next time for the test, right, which is going to be on Wednesday, be on time, right, be rested. Bring whatever formulas are online that you want to bring. There's a ton, but you don't need them all, okay? Just bring what you think you need. Then you can have one 8.5 by 11 sheet of paper, front and back, any sorts of steps, other formulas that maybe aren't easy to get to, and anything that you think would help, like curvature, right? That's a formula that is not on your formula sheets, I don't believe. Curvature, remember how to do arc length, blah, blah, whatever you want, you can put on there, you just can't have problems worked out, all right? Then, in addition to that, all right, bring anything else you have, notes, homework, things that you've been doing this semester, right? Because I think there will be an opportunity during the test, not for the whole time, but for at least a portion of the test, where I allow you to kind of be open note for just maybe 5-10 minutes. I think what I want to do is let you look at the test, let you work with it for a while, and then once you kind of know what you feel good about, what you don't, then I'll give you that kind of, all right, you get like 5-10 minutes to open your notes. You can kind of, like, oh yeah, okay, there it is. I know how to do that now. Kind of, just in case you have something happen where you freak out and don't remember, right? But if you don't bring anything with you, if you don't bring your notes, you don't bring your stuff, then, and if you have it on a tablet, that's okay. Like if you write your notes on there, that's okay. But yeah, that's the plan. Does that answer the question? All right. I don't know if it'll be at the beginning or at the end or when, maybe in the middle, I don't know yet. But just have your stuff just in case. All right, I have not made the test, so don't ask me how many questions because I don't know yet. I haven't made the test. So. One question? Yeah. All right, well, yeah, I mean, I'll hang out for a few more minutes. We don't really have enough time to start another problem, but I mean, you can see that these are similar. Find the point on a sphere closest or furthest from another point. So you have something you're trying to find the minimum of, and you have some constraints. We'll do that. We'll do those problems later. And guess what? You can have Lagrange with 2 constraints, not just 1. You can have Lagrange with 2 constraints. Now, we won't test on that, but it's possible. And it's in your homework. So, yeah, we will talk about that later. All right, if you have any questions over anything, I'll hang out for a few minutes. If not, I'm going to go to my office.
I have a question.
I'll be there as well. Yes.
So eventually you are going to give us like a take-home mini exam for Lagrange?
Yes, there will be something with Lagrange for you to take home. Yes.